Hello everyone, and welcome to TLE Eliminators PCD for CodeChef Starters round 189. Today we'll be looking at problems A to E of Division 2. So let's get right into it. Okay, so the first problem, nutrition cost. I suppose since this is the easier problem, most people would have done it, but let us go through it once anyways. Um, I'm sure there are multiple approaches to this, but I will describe the approach I did. Um, okay. There are n different food items, each providing an essential vitamin A and costing B of I. Okay, so each item provides an essential vitamin A of I and costs B of I. There is an integer parameter C, which represents the value of a single vitamin to you. Okay, you will buy some of the food items to maximize C times X minus Y, where X represents the number of distinct vitamin eaten. So keep it in mind that X represents distinct vitamins, not just vitamins, and Y represents the total cost of all food items. Find the maximum possible value. It is also possible to buy no food item at all, in which case the answer is simply zero. So how do we approach this? Okay, so let us first just write down what's there in the statement. Um, we have to maximize the value C times X minus Y. Okay, and X is the number of distinct items that we have, number of distinct vitamins, distinct vitamins, and Y is the total cost of the vitamins we took. Okay. So here we can see, since we are taking distinct vitamins, we will never take the same vitamin twice, right? So that's the first observation we can make. This is the first question. I guess most people solved it, so I won't spend too much time on it since I've gotten comments that I spent too much time on the first question. So yeah, um, for example, if we have a specific vitamin, 1, 2, 3, 1, 2. So these are the numbers of vitamins, or these are the values of A of I. And we also have uh, their costs, right? So we also have their costs, which is B of I. So let's say the first one costed 3, then this one costs 2, this one costs 1, this one costs 2, this one costs 3. Okay. So one thing which becomes very clear is if we have two vitamins which are the same but have different costs, right? If we have two vitamins which are the same but have different costs, we will always pick the one with the smaller cost. So for a particular vitamin, we will always pick the one with smaller cost. So in this case, if we want to pick the first item or the fourth item, since they are the same type of vitamin, they're both vitamin 1, we will choose the fourth one since it has a lower cost, it has only a cost of 2. And why are we doing this? Because the total cost is being negatively affecting our answer, right? We want to maximize this score. So that's why we choose the one with lower cost. Okay. And we can't choose both of them because we need distinct vitamins. So we need to choose only one of these two. And therefore we'll choose the one with lower cost. Okay. So this is first observation. And second observation is um, if we sort, if we sort mm, vitamins by cost, by minimum cost. So if we sort vitamins by minimum cost, what do I mean? So here minimum cost of vitamin 1 is 2, minimum cost of vitamin 2 is 2, and minimum cost of vitamin 3 is 1. So what we will do is we'll sort these costs. So we saw that minimum cost of vitamin 1 was 2, minimum cost of vitamin 2 was 2, minimum cost of vitamin 3 was 1. So we have these costs and we'll sort them. So we'll get a final array which looks like 1, 2, 2, right? So the idea is our value, our value, like uh, the required value, either we take, let's say, one vitamin or two vitamins or three vitamins, right? So our value will be some prefix of these. Our value of vitamins to pick is some prefix of this. And why is that? Because by picking each vitamin, we are adding C to the cost, and like we are adding C to the score, I guess. You can say adding C to the score. Score. What is score? Score is what I'm calling the value of this. So we want to maximize this, so I'm calling it our score. We're adding C to the value of score, and we are subtracting the cost of the vitamin from the score. All right. So in this case, let's say our given C value was, let's say our given C value was 1. Okay. So then basically, since we know that the vitamins costs in sorted order are 1, 2, 2, what this means is if we take the first vitamin, our score will increase by 1 and decrease by 1 because we are adding Cx, right? So we're adding C one time for this and we're subtracting 1 because that is the cost. But now we cannot add the next element. And why can't we add the next element? Because here if we add C and subtract 2, which is the cost, we'll get a negative number. So this is decreasing our score. So basically, for all these elements, what we have done is if we have that, we can subtract C from all these elements and we can pick the ones which are less than or which are greater than or equal to 0. So for example, if our C was, let's say, 2, for the same test case, if our C was, let's say, 2, then the array would look something like this. It would be, uh, okay, wait, no, just a second. Um, yeah, this should be actually C minus the cost. Sorry about that. It should be C minus the cost. So this will look like C minus 1, C minus 2, C minus 2. So it will be 0. This will be minus 1, minus 1. Yeah. So here we will have again 2 minus 1, 2 minus 2, 2 minus 2. So taking the first vitamin, taking the, actually it was the third vitamin, yeah, but taking this vitamin which was first in the sorted order, that gives us a score increase of 1 and the other two give us a score increase of 0. So basically we will choose any vitamins which give us a positive score increase. All right. So you can do this in many ways. So one way is simply uh, method 1 for the input array, remove the, like remove like for each vitamin you find, for each vitamin, for each vitamin, find the minimum cost, find minimum cost, then calculate C minus the cost. So C minus B of I for each vitamin, for each vitamin. Then sum the positive values. So this is the one of the methods you can do it, and this seems to be the most clean method. Another method which I had implemented during the contest, because during the contest you don't always come up with the best method. So the method I had done was, first step is the same, find minimum cost for each vitamin, for each vitamin, and sort them, sort them, and choose a prefix, a suitable prefix of the vitamins. Okay. So what would the code for this look like? Well, we can store our input as a map. So we can have a map where the first value of the map will be the vitamin, and the second value of the map will be the minimum cost for that vitamin. So if we want to take this input, it will look something like this. So here we define our array A, we take in all the values of A, then we create a map, and inside that we we take in our value X, which is the cost for this current A of I vitamin. Then if the map already contains A of I, then we simply take map of A of I equals minimum of map of A of I and X. Otherwise we set map of A of I to X. So in this way, for every vitamin, we know the minimum cost to buy that vitamin. And then after that, once we have done this, so if we follow the first method which I described, what we can do is we can define our answer as 0, and then uh, what we can do is, for every element in the map, if we can add to the answer, like if the value of C minus the cost, right? So Y is the minimum cost, C is the value we're gaining. If this is greater than 0, we can add this to the answer, and then finally we can output the answer. So this is one way of doing it. And the way I had done it in my code, because I was in a bit of a hurry and did not think that much, I had sorted the values, and then I chose the prefix. I chose the prefix which was giving me the best answer. So you can do it either way. So is that explanation understandable? Let's go to the next question. Okay. Should I go to the next question? Doubt. Okay. Go ahead, please ask. You can put it on the chat, or you can unmute and talk. There's no either way. Okay. Yeah. I'll just make it bigger. Yeah, my code is open. So this method is not the best method. Like the method which I explained right now is the best. But here what I'm doing is, um, I'm assuming that I take some prefix of my array. So I'm trying all the prefixes from I equals 0 to the size of the vitamin. And I'm taking the C times I plus 1 means I'm imagining that I took this prefix and I'm subtracting the cost of taking that prefix. And I'm finding max over all the prefix. Which line did you have a doubt in? Here y is representing the cost. Let me see. Yes, yes. Here y is representing the cost, yes. When you take x and y from the map, x will be the vitamin number and y will be the minimum cost. So that's what we're pushing back in the vector. Yeah. So the answer to the question is yes. All right. Okay, moving on to the next question. Our next question is create binary string, which is somewhat easier than this, to be honest, at least to code. Okay, let us write question B. Create binary string. Okay. You want to make a binary string S of length n, and you will be paid according to the following rules. So basically, you have full control over the string, but you will be paid according to some rules. For each occurrence of the subsequence 0 in S, you are paid A coins. Fine. That just means the number of zeros which are there in S. For each zero, I will be paid A coins. For each occurrence of the subsequence 1 in S, you are paid B coins. Okay. For each occurrence of the subsequence 0, 1 in S, you are paid C coins. And for each occurrence of the subsequence 1, 0 in S, you are paid D coins. Okay. You want to maximize the number of coins you get, find the maximum value. So we don't even need to print the subsequence. We just need to print the maximum value which we get. All right. So let us think about how to do this. First, let us consider the number of zeros and ones. Okay. So first idea is, so this idea we can do even before actually writing an example. Just from reading the statement, you can say that you have to make binary string of length n, right? Binary string of length n. So you have to make a binary string of length n. So let's say there's number of zeros is z. So I'll call that z, and number of ones is o. Okay. So number of zeros plus number of ones will be n, right? And the the reward you're getting from this, or the coins you're getting, will simply be z times a plus ones time b. Okay. So from the start itself, we can tell that if we have this much zeros and this much ones, then we will get this many coins. And we can also say zeros plus ones equals n. So that is the first observation we can make directly off of the question. Now to make observation 2, which is all zeros and ones can be grouped together. And let us see why am I saying this? Together. Yeah. So okay, so we need to understand the meaning of subsequence, right? So here it is given, we have a string like 0, 1, 0, 1, right? So how many occurrences of 0, 1 is there? Because each occurrence of 0, 1 we get C coins, correct? So if we observe, we have a 0, 1 here. We also have another 0, 1 with these two. And we also have a 0, 1 with these two. So there are total 3 occurrences of 0, 1. So 0, 1 here, 0, 1 here, and 0, 1 here. Okay. Sorry, here and here and here. Right. So why am I saying all the zeros and ones can be grouped together? Well, the reason is, consider the case 1. Okay. Case 1, we have C is greater than D. Okay. So, and let us say the number of zeros and number of ones are fixed. Okay, and number of ones be some fixed for the optimal answer. For optimal answer. So like the final answer will have some fixed number of zeros and number of ones, right? So let us just assume that those are fixed. Then let's say there were 5 zeros and 4 ones. Okay. So we do something like this. Okay. Now if there are 5 zeros and 4 ones, and let's consider some string like this. So every time I have a 0 1, I get C amount of coins. Fine. And every time I have a 1 0, I get D amount of coins. And the thing is, every time I have a 0 1, that means I'm losing an opportunity to have a 1 0. Because if I swap the positions of this 0 and 1, I can get a 1 0, right? Similarly, if I had a 1 0, I'm losing the opportunity to get a 0 1, because if I swap these two positions, the rest of the string remains the same, the rest of the cost remains the same, but I can switch a 1 0 and 0 1. So my cost goes from D to C. Now the idea is if C is greater than D, then basically we have a 1 0 over here. But if we swap these two, we'll have 0 and 1. And what happens to the cost? Well, here the cost of these two, which they're contributing, is D, right? This subsequence 1 0 is contributing a cost of D. But if we swap these two, then they will contribute a cost of C, and everything else remains the same. Now the thing is, we know that C is greater than D. So obviously it is better to swap them. In fact, it is better to swap all 1 zeros to 0 ones. So if we do that, what happens? All the zeros will come to one side and all the ones will come to the other side. And what we'll have? We'll have all the zeros here and all the ones here. So all the pairs we can form will be between 0 and 1. All the pairs we can form will be between 0 and 1. And why is that? Well, we know that C, which is the cost of 0 1, is greater than the cost of 1 0. So therefore, if we have some Z zeros and O ones, then it is best to put zeros before the ones in this case. Okay. Now in the case 2, if D is greater than C, then it is better to have 1 0 as substring compared to having 0 1 as substring. So in this case, if there is some fixed number of zeros and ones in the answer, and obviously there'll be some fixed number of zeros and ones in the final answer, then it is better to move all the ones to the start and all the zeros to the end. And the reason for this is because now we'll have all 1 0 pairs. Okay. So that's why our final answer will always look like this. All the zeros and ones will be grouped together in one block. Either it will be all zeros followed by all ones, or all ones followed by all zeros. So these are our two possible answers for this question. Okay. So now let us go to the third point. And the third point is assume there are Z zeros. Okay. Then what is the cost we can make? If there are Z zeros, then already we got Z times A plus N minus Z times B, because this is the number of ones. So therefore we got Z times A plus N minus Z times B. Now there are two options. Either zeros are before ones or ones are before zeros. Okay. So if all the zeros are before the ones, then every zero can be paired with every one. So we get a cost of C times 0 times 1. So this is if the zeros are before the ones. So this is our case 1. Okay. And our case 2, the first part remains the exact same because they're same number of zeros. Okay. Now what happens? These two get, so if we put ones before zeros, so this is zeros before ones, and this is ones before zeros. In this case, we will get D times 0 times 1 as our answer, because the number of pairs remain the same between zeros and ones. But the cost we are getting becomes D because we have made ones before all the zeros. So now, since the value of zeros is between 0 to n, we can try all the values of z in these two equations and see where we are getting our maximum. So what is our final idea? Our final idea for all z, which is number of zeros, in 0 till n, we answer will be max of answer, the first value. So z times a plus n minus z times b plus c times z times 0. And again, answer will be max of answer times z times a, same thing. So our answer will be the max of these two and across all possible values of z. And that is all we need to implement in the code. It's a very basic big O of n code. We set our answer to be 0 initially because we want to find maximum answer. We start at z equals 0, number of zeros is 0, and go all the way till n. Then we take max of these two equations, and finally we give as output our answer. The time complexity for this would be big O of n itself because it's just one loop. Okay. Why can't we pair them as 1 0 1 0 0 1 0? Okay, I will I'll explain that, but go over it once again. Why don't we do mixed pairing? Okay, so the idea for this is if we have something like this, right? And I told you either C will be greater than D or D will be greater than C. If they're equal, then it doesn't even matter. It doesn't matter. If D equals C, then the order will not matter, right? So um yeah. So the idea is that let's say C was greater than D. So then what would happen? Having a 0 1, right? Having a 0 1 is better than 1 0. Why? Because let's say C was 10, D was 5. Okay. Then here having a 0 1 is giving us 10, but having a 1 0 is giving us 5. Right. So what happens if we swap these two? If we swap these two, then we get a sequence which looks something like this. Then we get something like this. And what happened earlier? Earlier we had from D, we were getting a 5, but now from C we are getting a 10. So our score increased by plus 5. And we can keep repeatedly swapping this way until the sequence becomes all the zeros followed by all the ones. And the reason is simply that C is better than D. So that's why we want more of C pairs rather than D pairs. And in fact, we make all the pairs into C pairs instead of D pairs. I hope that was understandable, Ishan. It's a greedy idea, and we greedily want zero ones more than one zeros. And the reason is C is greater than D. If D was greater than C, if D was greater than C, then we would want the other way around. We would want 1 0 greater than 0 1. And that is the idea. Okay, I hope that was understandable. Let's move on to the third question. Avoid primes. Okay, this is a very constructive question. So it depends a bit on your making cases and finding patterns. Let us read the question. You are given an integer n and you must construct a permutation p in 1 and n. Okay, so the normal permutation. So you must construct a permutation of size n. You define f of p as the number of integers such that the minimum of p of I, comma p of I plus 1 is prime. So the minimum of two consecutive uh, values of the permutation, if they are prime, then we count that in our f of p. Note that 1 is not considered a prime integer. For example, f of 4, 2, 1, 6, 5, 3 is 3 because indexes 1, 4, and 5 satisfy the condition. Find a permutation with minimum value of f of p. If multiple permutations exist, you can print any. So let us decipher what this question means. Let us take their example itself. So their example was something like this. It's 4, 2, 1, 6, 5, 3. And this is some permutation of integers from 1 to n. So this is our permutation. Now what are we doing to this permutation? What we're doing here is we are finding how many adjacent elements, p of I and p of I plus 1, the minimum of them is prime. So let us check that. So if we take two adjacent elements, 2 and 4, the minimum of 2 and 4, so p of 0 plus 1, so this will be minimum of 2 and 4 is 2. Okay, so basically the minimum is 2 and 2 is a prime number. 2 is a prime number. So we can say that this will contribute to our f of p. So this is one valid such index. Okay. Now let us check the next index. What about 2 and 1? The minimum of 2 and 1 is 1, which is not a prime. So this index is not valid, right? This value of I is not valid. Okay. So now let's check minimum of 1 and 6. And again, the minimum is 1, which is not prime. So this is also not valid and we move on. Now 6 and 5, the minimum of these two is 5 and 5 is a prime. So here also we can say that it is valid. And this forms our second valid pair. So this is our second valid index or pair of numbers. Okay, now let us consider 5 and 3. The minimum of 5 and 3 is 3, and we can say that 3 is a prime number. So therefore, it will be valid here as well. So this is the third position where this property is valid. So we can say that for this permutation, the function f of p will return 3 because there are three positions such that the adjacent element's minimum is a prime number. Okay. So that is the basic idea. Now we want to find arrangement such that the value of f of p becomes less. So here is a rough intuition. So rough intuition. Basically, we want to surround primes. So want to surround primes with non-prime numbers that are lesser than it. So basically in the final permutation, we have to make it in such a way that we want non-prime numbers that are lesser than it to be next to it. What do I mean by that? Let us see with an example. So if I take an example, let's say n equals 3. Okay. So what are the possible permutations we can have for n equals 3? Well, we can have 1, 2, 3. Then we can have 2, 1, 3. Then we can have, let's say, 2, 3, 1. Of course, we can have the reflection of all of these also. But these are the three cases. The answer will be same if you reverse all the permutations. So let us count how many we get in each case. So here minimum of 1 and 2 is 1, which is not a prime. But here minimum of 2 and 3 is 2, which is a prime. So for this permutation, f of p will be 1. Now here minimum of 2 and 1 is 1, which is not a prime. Minimum of 1 and 3 is 1, which is not a prime. So here f of p is 0. Okay. And then here we can see that again minimum of 2 and 3 is 2, which is a prime. So the answer for this will be f of p is 1. So clearly for n equals 3, this is the only valid permutation, this one, and we should print this one out. Fine. Of course, we can reverse these permutations, and that will give us 3 more, but they will also have the same answers as the original. Okay. So what about n equals 4? And now we're trying different values of n, trying to find a pattern. Fine. So this is about a bit of, your guessing skills, your constructive skill, and your IQ, you could say. But let's try. So we already know 1, 2, 3, 4 will probably not be it, because here it's a prime, and then here again it's another prime. So f of p is 2, right? So let us try to figure out some better way. Well, what we can do here is we can again do something like 3, uh, we can do something like 2, and then we can put a 1, and we can put 3, and we can put 4. And here only at one position is it getting violated, right? Like only at one position we are having minimum is prime, like minimum of 3 and 4 is prime. You can see that in the other positions this is not happening. So we can say that for 4, the minimum f of p we can get is 1, and that this is one of the valid answers for n equals 4. Okay, but we have not found a pattern yet. All right. So let's try some large number like n equals 10. Fine. So if you keep trying some patterns, what you will see is what we can do for numbers which are greater than, let's say, 5, right? So when you write, let's say, so if you write like for n less than equal to 4, we can just directly hard code it. But when you write, let's say above 5, right? You start seeing that always f of p will be 1, because if you try for something like n equals 6, in fact, even n equals 4 also, you're never able to reduce it to lesser than 1. But for n equals 6, we can find a pattern which works and gives us exactly 1 as our answer. And it is 3, 2, 1. And so here we can see that the condition is being, triggered. Min of 2 and 3 is 2, which is a prime. But then after this, we can make sure that it never triggers. And how can we do that? What we can do is we can put 5 here and 6 here. Okay. And then from the n equals 6, we can solve for every higher value from n equals 6. And how can we do that? Uh, okay, wait. Uh, 3, 2, 1, and then uh, sorry, I completely forgot to add 4 here. Yeah. So what we get is 5, 4, 6. Yeah. So from, and for n equals 5, obviously we can write 3, 2, 1, 5, 4. Right. So we have written for 3, 4, 5, and 6. Right. So from this point onwards, from roughly n equals 5 or n equals 6, we can start getting a pattern. And the pattern is this. For n equals 7, we get the same 3, 2, 1, 5, 4, 6, and then 7. And the idea is, yeah, and the idea is what we are doing for every next odd number. So every next odd number we are placing between the previous two evens. So the previous even to 7 was 6 and the previous even to 6 was 4, right? So these are the previous two evens of 7 and we are placing it between that. Okay, so 5 is being placed between 1 and 4, and so that way its effect of being prime is being cancelled, because here 4 is a smaller number and not prime, 1 is a smaller number and not prime, and then every new prime number which we get, or every new odd number itself which we get, we will be placing it between the previous two evens. And I'm sure there may be other patterns to solve this, but this is the pattern which I found. So let's say we had to go to 8. So for that, we would simply add 8 over here. Okay, but if we had to go to 9, then we would add 3, 2, 1, 5, 4, 7, 6, 9, 8. And again, 9 is being placed between the previous two evens. And now you'll ask, why are we doing this? Why are we doing this? And the reason is, even number is always not prime once it's greater than 2, of course. Even number greater than 2 is always not prime since it's divisible by 2. And you remember our original intuition was we want to surround primes with non-primes that are lesser than it. So even numbers are always not prime. So only odd numbers are the possible primes. So what we will do for every odd number from some point onwards is basically the previous two even numbers will surround it. So that way we can make sure that these will not trigger the rule. These will not have the minimum of them as prime, because the minimum of them will always be an even number, which is not a prime. Right. So here it will be 10. And so starting from like 4 onwards, 4, 7 onwards. So we can have 4 and 7. Right. So this part you can ignore it. Like this part will come back to later, or we already discussed that part actually. Starting from this point onwards, we can follow this pattern that we put the next odd number. So next will be 13, and then we can put the next even number 12. And this way, every odd number is always being surrounded by two smaller even numbers, and we can repeat this pattern. And for the starting position, there is no way to avoid having at least one conflict. So one way to put the starting is putting it 3, 2, 1, 5, and just before this. So we can put 3, 2, 1, 5. So the first four values will be 3, 2, 1, 5. And why is that? Because here 5 is an odd number, but it does not have, you know, an even number. There's not enough even numbers to put over here, non-prime even numbers. But what we are doing here is we're putting 1, since 1 is not prime, and that way we're making sure that 5 also does not conflict. Then only conflict will be 3 and 2, where minimum of 3 and 2 is 2. So for all n greater than or equal to 4, we can solve it this way, or greater than equal to 5 actually, since there needs to be at least 5 for this pattern. We can solve it this way. Our idea will be put 3, 2, 1, 5, then put the next even number 4, the next odd number 7, and keep alternating in that pattern. Okay. For n less than equal to 4, we can simply hard code, or you can find some pattern for that. The pattern is already given in the samples, because in the samples they have given us for small values like 2, 3. So we can simply write 1, 2, 2, 1, 3, and 2, 1, 3, 4. So hard code. So we can just write 2, 1, 3, 4 and 2, 1, 3, 2, 1, 1. So you can simply hard code these 4 cases. I hope that was understandable. It's a constructive problem, so you need a intuition for it. But yeah, basically what we're doing is for every odd numbers are the only possible primes. So for every odd number, we are surrounding it with two smaller even numbers. to make sure that they don't form a pair such that the minimum will be prime, right? Because these two cannot be primes because they're even, and this one will not trigger because even if it's a prime, we made sure that these two are smaller. So does that make sense? What if we add 1 and then add all primes up to n? And then in between rest numbers? Won't we getting the answer? Okay, yeah, that might work. But the thing is, um, yeah, that because the number of composite numbers grows much faster than number of prime numbers. So that idea will also work. But the thing is, for very small values, it will fail. Like for example, if we add a 1 and n is equal to 3, right? So n is equal to 3 and we add a 1, then we add all the primes. We have nothing to put in between right now, correct? So yeah, at some point that will start working, I guess. We can see which end that starts working. So so uh, one. Okay, to be completely honest, that also works. Yeah, that also works. So it's a nice idea. But to find composite and prime numbers, you will need some method. Yeah, for n greater than equal to 3, it's working. So nice method, yes. But again, to find primes and composites, you might need to write a sieve. So that would add a little bit to the complexity. But yeah, that's also a perfectly all right way to do it. Okay. So maybe I was missing that during the contest, I guess. So I'll just discuss the time complexity. Uh, since we're just printing a pattern, and to be honest, any pattern you find, there'll probably be like 5 other different ways you can find the pattern. This was the way I found the pattern. The time complexity is big O of n. If you are actually using a sieve to find the primes and then put things in between the primes, then it'll be obviously the complexity of the sieve plus n. And the sieve will be like something like n log n or something, depending on which sieve you're using. Yeah. So let us see how to implement this. So for n equals to 4, you can just print all the 4 cases. The way I did it was I found a pattern in that also. I just saw that if you write 1, 2, 3, 4, if you write the numbers 1, 2, 3, 4, and then swap the first two, you will get the answers for the 4. Like for 1, it will simply be 1. For 2, it will be 2, 1 is a valid answer. Then 2, 1, 3 is valid answer. 2, 1, 3, 4 is valid answer. In which first two are swapped and other numbers are same. So that's the way I wrote the code for this, for the n less than equal to 4. Then for n greater than or equal to 4, I'm writing my pattern. I'm writing it as 3, 2, 1. And then after that, I'm simply filling 5, the next odd number, 4, the next even number. Then so basically I fill all the odd numbers first. So I do 5, 7, 9, and then 6, 4, 6, right? And like that. And then if we do filling in this way, then if the n is even, then the last number will be 1 extra. So we can simply convert it like here for n equals 8. If we fill like this odd, odd, even, even, the last number should be converted to an even. We convert it to even and then we print it. So basically we're printing that pattern which I just described. That's all for the code for this. Time complexity is big O of n. And I think this is a fairly simple construction. Yeah. Okay, if there are any doubts, you can drop it in the chat right now. Otherwise, we can move on. How to practice such problems? Obviously, if you do more constructive problems, more number theory related problems, you will get good at picking patterns. These types of questions just test your pattern picking ability. Okay, clear. Let's move on to the fourth question. Sortable subarrays. Yeah, this one took me some time because I misread the question, but yeah, it is a simple question itself. In fact, if you don't like constructives, then this might have been easier than the previous one also. Okay. So here we are already given that uh, sum of n over all test cases is less than 500. So that's the first thing they said because the easy version of the problem. Okay. And array A is called sortable if it can be sorted in strictly ascending order. Note that it does not mean ascending order, it says strictly ascending. So A of I must be less than A of 2, A of 1 must be less than A of 2 and so on. Exactly less. It can't be equal also. So an array A is called sortable if it can be sorted in strictly ascending order with the use of the following operation any number of times. What is this operation? The operation is choose any index I and a positive integer x, then update A of I to A of I mod x. Okay. So what is, let's say our operation, let's say we had an array like 3, 4, 2, 1. So we could take any element, choose some modulo. It can be any modulo, 3, 2, something, anything we can choose. So let us do 4 mod 3 and we can change it to 1. So instead of 4, we can write 1 here. Okay. So now our task is to find the number of sortable subarrays of A. So our task is to find number of sortable subarrays. And again, sortable is defined that we can sort using this operation. Sortable subarray. So this is what we need to find. How many pairs L of R exist such that this thing, the subarray is sortable. Okay. So we're given 100 test cases, n is 50 each for a test case. Sum of n over all test cases is 500. If sum of n over all test cases is 500, what will be the expected complexity? We can say that the expected complexity should be, yeah, since n equals 500, at least sum of n over all test cases is 500, expected complexity should be something like n cubed. Obviously, we can solve better than n cubed also, but for the easy version of the problem, they expect something like n cubed from us. And we'll try for something like that. First, let us consider having a whole array and seeing how we can make it sortable or not. Okay. So let us consider the operation itself. Our operation. Our operation basically means given A of I, what we are doing is we are taking A of I mod x, where we can choose our x, and then we make the value of A of I into A of I mod x. So let us ask the obvious question. What are possible values of A of I? Okay. So what are the possible values of A of I after using the operation? Well, let us take a concrete example. Let's say A of I was 10. So what are the possible values we can find if we do 10 mod something? Well, obviously 10 mod 1 is 0, right? Now 10 mod 2 is again 0. 10 mod 3 is 1. 10 mod 4, 10 mod 5. So right now we're just experimenting and we're trying to see what are the values we can get, right? 10 mod. Obviously taking mod of a larger number will not make any sense because then it will be the same value itself. So 10 mod 4 is 2, 10 mod 5 is 0 again, 10 mod 6 will be 4, 7, 8, 9, 10, 0, 1, 2, 3. Okay. So what can we observe here? Well, we can observe that if you take n mod n minus 1, obviously you will get 1, right? Similarly, we get n minus n minus 2, n mod n minus 2, we get 2, and so on. Because why are we getting this? Because if we have n mod n minus k, all right, and here this value is greater than, let's say, n by 2, okay, it is greater than n by 2, then what we get is we get basically n minus k plus k equals n, right? So that plus k we are getting out from here, basically. Because, for example, if you take the example of 10 mod 6, well, 6 is simply 10 minus 4, right? And if we add 4 to 6, we get 10. Therefore, we can say directly that 10 mod 6 is 4. And what about numbers smaller than that? Well, if you take any, so this is n mod n minus n by 2. So for all numbers x where like the x is less than or equal to n by 2, then obviously the mod value will also be less than or equal to, and the mod value will be less than n by 2, right? So all these mod values which are where x is less than n by 2, the mod value will also be less than n by 2. Why? Because if you take mod of some value with x, you will get from 0 to x minus 1 only the values. If we take a mod of a number with x, then the output we get is between 0 and x minus 1. So therefore, for all numbers less than or equal to n by 2, the output must be somewhere between 0 and n by 2 minus 1. Correct? Similarly, above here, above n by 2, we can see the straightforward pattern. Because if we take n mod something which is greater than n by 2, then simply we need to add that much as remainder to get the value. So we can write it like this formally. Let us write it formally. Formally, so for a of I mod x, if x is less than or equal to, if x is less than or equal to a of I by 2, then a of I mod x will be less than a of I by 2, and otherwise x is greater than a of I by 2. And what will happen? Then obviously 2x will be greater than a of I, right? So remainder of a of I, so remainder of a of I with x will simply be b a of I minus x. So because we need to add a of I minus x to get a of I, the remainder with x will simply be this. So the possible values, so possible values of a of I mod x are simply everything from 0, 1, 2, all the way to a number y, where y is the smallest integer, less than a of I by 2. And this is our key idea, that the possible values of a of I mod x under our operation are this, and all these possible values we can create the same way I described right now. So these are all the possible values, and we can create all of these possible values. Okay. So what does this mean in our example? So if we have an array, now let us take an example itself. Let us take a 5, 3, 1, 4, 2, 1, 1. So 5, 3, 1, 4, 2, 1, 1. What are the possible values we can make 5? Well, one way is to leave it unchanged. So 5 is a possible value. The other values we can make is 0, 1, and 2. We can't make 3 because it's greater than 5 by 2. So these are the possible values we can convert it to. Similarly, what are the possible values? We can make 3. We can convert it to 0 and 1. We can't convert it to 2, and we can only convert it to, we can convert it to itself, of course. Like we can leave it unchanged. 1 will either be 0 or it'll be itself. And this is under any operation we do, right? Even if we do operations repeatedly, the numbers can only get smaller. So our possible numbers we can reach does not change. For 4, we get the possible numbers as 0, 1. We won't even get 2 because it should be less than n by less than a of I by 2, not less than equal to. So we get this as our possible values. Similarly, here we get 0. We don't get 1. We get 2. 0, 1, 0, 1. So these are the possible values we can convert each element to. And a simple way of saying it is, we can convert it to anything which is a of I by, in C++, we can write it like this because automatically it does floor, right? So we can convert it to any number less than or equal to this value using the mod operation, or it, or make the number stay the same, or stay the same. Okay. Now we are ready to solve the original problem. And how will we solve it? So since recall that we can go up to n cube complexity for each subarray, which we can run 2 loops from I to 2 loops from all possible values of I and j, right? So all values of I and j. We can do this in n square. We will check if it is a sortable subarray or not. We will check if it is sortable or not. And how will we check if it is sortable? We will describe the following greedy idea. So given some subarray, so this is L and R, and there are some numbers here. Let's say 5, 4, 2, 8, 7, 1. Okay. How will we check if this is sortable or not? Well, we know that we can make 5 into 0, 1, 2, or 5, right? So obviously, let us make it the smallest value it can be. Why? Idea is make every element smallest value. Make every element smallest possible value. Why? Because now to sort, we need everything in strictly ascending order, right? We need this less than this, less than this, less than this. So obviously we can make this one smaller. Like obviously it could be a larger value as well, but we'll try to make it as small as possible. So our sortable like subarray extends as much as it is to the right side. Okay. Similarly, we can do for 4. So since we made 5 into a 0, 4, we can see the possible values are 0, 1, and 4. So we'll make 4 into a 1 because it has to be greater than the previous element. What about 2? The possible values of 2 are 0, 1. Sorry, the possible values of 2 are 0 and 2. So obviously 0 is not possible. So we make it stay the same. We make it stay the same as 2. So we convert this to itself, which is 2. Now for 8, the possible values are 0, 1, 2, 3, 8. So we convert 3 since it is bigger than the previous element. And that is the smallest possible value bigger than the previous element. So we convert to 3. Now what about 7? For 7, we have 0, 1, 2, 3, 4, 0, 1, 2, 3, 7, right? We can't convert 4. So 4 is not possible, so we leave it the same and we make this a 7 itself. Here 1 has 2 options, 0 and 1. But since neither 0 and 1 are satisfying, not possible. Since 7 is greater than either 0 or 1. And we know that 7 is the smallest possible value we could have had here. So 7 is greater than 0 and 1. We can say that for this subarray, it is not possible. Although up till here, it was possible. Up till here, all the subarrays, it was possible because we were able to continue this pattern, but here it is not possible. So what was our idea again? Our idea was, full idea was, consider all subarrays a range of value after operation is 0, 1, so on until it reaches a of I minus 1 by 2. And of course, it can stay the same. So these are all the range of values of operation. Choose greedily smallest value in the range and see if it is sortable. So for each subarray, we can check this. Okay. Now one more, we don't require it since I think n is 500, so even n cube should pass. But one more optimization we can do, and we can make this n squared. And how can we make this n squared? Well, simply if at some point, if the pattern breaks, like here the pattern broke, then we can say that this subarray is valid, this subarray is valid, this subarray is valid, till here and here it's valid, right? But after that, all the subarrays will become invalid. So we can just keep building this pattern in our second loop itself, and we can implement this, can be implemented in big O of n square itself. Okay, it can be implemented in big O of n square. Although I think there is enough time complexity to consider all subarrays, and even inside the subarrays check how to implement this. So let us have a look at the code. So what we do here is we take in n, we take in our vector, we take in our values. Okay. Answer is 0. So that is the number of subarrays, and I set it to be 0. And what is previous? Previous is my previous is the value of my previous element, like the smallest value I could make it. Fine. And what I do is for each element from L all the way to N. So these are the values of the right values I'm putting. These are the left values. These are the right values. If this smallest value a of r minus I by 2, if this is greater than the previous value, then we simply increase the previous value and we increase our answer because we know we got a new subarray. Otherwise, if a of r is greater than previous, we set our previous to a of r, because what does this mean? This means that the value is less than or equal to half of it was not satisfying. So we're trying the value itself, in which case again answer increases and we go to the next. Otherwise we break. And finally we print the final answer. So if this is confusing, let me just dry run it on some example. So let's take some example and dry run it. Okay, let us try this example itself. 5, 3, 1, 4, 2, 1, 1. Okay, so our I is 0 and j starts at I itself. So here we compare what is the maximum so far. Initially, the maximum so far is -1 itself. That is my variable previous, which I kept. So in the start, we're keeping it -1 because all the values should be greater. Now, what are the range of values of 5? The range of values of 5 are this, correct? So we can see that the value of previous plus 1. We're trying to increase previous by 1. So if previous here was -1, we're trying to increase previous here to 0. So we're trying to make 5 into a 0. And we can see that we can indeed make it into a 0. So we assume that for this subarray, it has become 0 and we continue on. All right. And then what about 3? Here we can try. So 3 has the possible values. So here we can add 1 to our answer because this thing satisfies. So answer plus plus. So our current answer will be equal to 1. Fine. So now j will go plus plus, so j plus plus, and we go to the next iteration of our loop. So now we're at 5, 3. Here our value of previous is 0. Here our value of previous is 0. And here again we check if, what are the range of values? The range of values are 0, 1, 3. And 3 minus 1 by 2, that is 1. Yes. So we check if 1 is greater than previous. So 1 is indeed greater than 0. So we can do previous plus plus and set that, assume that that is our current value. So basically what we're doing is we're assigning the value of 1 to 3. So we set this to 1. This is 0. Now for this, what is our value of previous? Our value of previous is 1. Correct? Our value of previous is 1. And our answer has become 2 now because this also was valid. Now here our previous is 1 and our possible values for this are 0, 1. So what happens is this part fails because it's not less than half. This part also fails because it's not less than 1 itself. So we break. So this value of I, which is I equals 0, breaks out and we have answer 2. Then we can continue onwards with I equals 1. So we start with I equals 1 and we try to extend it as much as possible. And then again, we start from I equals 2. We take the value of 0 over here, try the value of 1 over here, take value of 2 over here, stops. So we add 3 to our answer from this position of I, and so on for all the values of I. So basically what our idea again is, our idea is make it as small as possible. And how small can it be? You can try to see if it fits here, in which case it will simply be previous plus plus. Otherwise, we can try to see if this is greater than previous, then we'll set this to the previous. Otherwise, it's not possible and we break. And we can do this in O of n squared. Is that understandable? Yeah. Not less than equal to n by 2. The value should be less than equal to n minus 1 by 2 because consider for something like n, or actually a of I, right? Should be a of I by 2. A of I minus 1 by 2. Yeah, because if let's say a of I was 6, if it's an even number, what happens is 0, 1, 2, 6 are the valid ideas, not 3, because 6 mod 3 will be 0. So yeah, it should be less than or equal to a of I minus 1 by 2. Okay. So I hope that was understandable. Let's move on to the final question. If there are any doubts, I mean, not final question, but final question for this session. If there are any doubts, you can put in the chat. Yeah, clear. Cool. One doubt. Sure, go ahead. Go ahead, ask it. Yes. It's from the subsequence question. Which one? Are you talking about question A or binary string? Which one are you talking about, B or A? Question B, okay. What do we do if asked to print the subsequence? Okay, so that also we can do fairly easily. We are going from z equals 0 to z less than equal to n, right? And we are trying out which is giving our maximum value. So what we can do is, so let me just write doubt related to B. If we had to print the maximum string, if we had to print the string, what we would do is, since we are going in this loop and we are checking the number of zeros and ones, right? Whenever we hit a maximum, like at which point we hit the maximum, at the point we hit maximum, we can store number of zeros, and we can also store whether it was hit with 0 1 case or 1 0 case. So we can store both of these. All right. And how can we do this? We can basically write, instead of using max function, we can write if basically this expression z times a plus Okay, 1 times b plus z times 0 times c, right? So if this expression is greater than our answer, then we can set answer equals this, right? We can also set uh, max ka 0. So how many zeros are there in the max as z? So that way we will know that these many zeros made us reach our max. And if we want, we can also set a Boolean value, like a bool value, whether it was 0, 1 or 1, 0 case, right? So this was a 0, 1 case. So we can set, let's say we can set flag equals true to make sure that 0, 1 case. Flag equals false means it's 1, 0 case. So then once we are done with the loop, we can simply put those many zeros in the start and those many ones after, and we can make a string and we can print it out if they had asked us to print it. Okay. Yeah. All right. Problem E. Number box. Okay, so this is a slightly harder one compared to the previous ones. So let us read the question. You are given an array A of n integers and an integer k such that 1 is less than A of 5 less than k. Okay. And each integer 1, comma 2 all the way to k appears at least once in the array A. Okay. Suppose we start at some position S and solve the following problem. So they've written it in a very complicated way, very formally. But I think we can just we can read this instead. It's understandable. So they want a sequence starting at S. So it should start at some position S in our array. Then the next element is an occurrence of 1. The next is an occurrence of 2. And next is an occurrence all the way till k. And we should find the sequence which minimizes the total distance. The starting position S is not fixed. So we should print the answer for each S from 1 to n. So what does this mean? Now let's have a look at the test cases and explain. Let us take this test case. N equals 9, k equals 4. Okay. Okay. And our array elements are 1, 3, 2, 2, 4, 3, 1, 2, 1. Now what it says is all the elements will be less than or equal to k. So as we can see, k is 4, right? So here 1 is less than or equal to 4. Similarly, 3 is less than or equal to 4, 2, 4. All of these are less than or equal to 4. So that is the given condition. And we're also given that each integer appears at least once. So 1 appears once, then 2 appears once, 3 appears once, 4 appears once. And like they can appear multiple times also. 3 is appearing twice, but they will appear at least once. So there'll be 1, 4, there'll be 1, 2, there'll be 1, 1, and that will always be the case. So what do we want to do here? We can try starting at every position S, and we should move to an occurrence of 1, then occurrence of 2, all the way till occurrence of k, and we should find a sequence which minimizes the distance. So let us assume our starting position S is 2. So let's say S equals 2, starting position is 2, and we start here. Fine. So what do we have to do here? We have to go first to an occurrence of 1. So either we can go here or we can go here. All right. So let's say we go to an occurrence of 1. The distance to this is 1 because the distance between these two are in the array is 1. Okay. Then from 1, we need to go to an occurrence of 2. So let us just go to this occurrence. And what is the distance for this? The distance for this is 2. Now again, we go to occurrence of 3 because that is the next in our list. We need to go from occurrence of 1 to 2 to 3 to 4. So this is also distance of 1. Now from 3, we go to occurrence of 4 and the distance is 1, 2, 3. Okay. And for this walk, which we did right here, what is the cost? The cost is 1 plus 1 plus 2 plus 3. So that cost is 6. Yeah, makes sense. Obviously, we can do any other walk, but we must always go like from 1 to 2 to 3 to 4 from our first element. So from this 3, we could have gone to this 1 itself. Then we could have gone like this 2, then 3, then 4. And what would be the cost? The cost would be 1, 2, 3, 4, 5, 6, 7. So this would be 7, be 1. This would be 2, and this would be 1 again. So the cost for this is 7, 8, 9, 10, 11. 11. So obviously the cost is much higher than previous time. And what they have said is for each starting position S, you need to print the answer. So for example, they gave us this array and we need to print this array, which is the answer for each starting position S. As you can see from the second position, the answer is 7, the same way we calculated. 7 means going here, then back here, then from 3 to 4. So the answer will be 7 at this position. What about at 1? If we start at 1, we can go like this to 2, to 3, and then to 4. What is the cost? It's 2 plus 1 plus 3. So the answer should be 6 at 1. And indeed it is 6 at 1. So how do we find this minimum cost quickly? At first, the problem seems very hard because let's say you start at some position. You can jump to any position you want. Like you want to jump to this one, you can jump to this one, you can jump here, right? You can jump anywhere. Similarly, let's say we were there somewhere in the middle of the process. So we had jumped to a 1, then from a 1, we can jump to this 2, to this 2, to this 2. And if we write a basic brute force, if we write a braided brute force and try to jump all positions, it will immediately TLE because what are the constraints? Let us have a look at the constraint. N is 10 power 5. So finally, we have like strong constraints for this problem. N goes up to 10 power 5. So we can't just brute force it. We need to find some clever way to do it. Okay. So after you think a little bit about the problem and you get some basic ideas like, okay, what if I try to DP? What if I try to, those kinds of things? We can get one way of viewing it. And one way of viewing it, which I'll tell you is, let us assume that we are in the current element, of our walk. Okay. We are in the current element of our walk. And what does that mean? So, and we find min cost to walk to K. So this is like an intermediate computation we're doing. And what does this mean? It means that at 3, instead of going to a 1, then 2, then 3, then 4, right? At 3, we just assume we want to go to 4. Fine. And we find the minimum cost to go to 4. Fine. At 2, what do we want? At 2, we don't say, okay, let's go from 2 to 1 to 3, then to 4, like that. From 2, we'll find the best part to a 3. So between these two 3s, which is giving me my best answer. Fine. Similarly, for this 2, I will try this 3 and this 3, and I will see which is giving me my best answer. And then what we can do once we have this, then we simply need to check from my element AI, what is my minimum cost to reach K? And we only need to check all the elements which have value AI plus 1, right? So from 2, we need to check 3. From 1, we need to check all the 2s. From 3, we need to check 4. So we need to check all the elements which have value AI plus 1, correct? For element AI, check elements AI plus 1. Yeah. Check elements with value AI plus 1. With value AI. Check elements with value of AI plus 1, right? And whichever gives you minimum, So first we need distance, of course. So let's say the whichever gives minimum cost, we can store that, right? So obviously this is a kind of DP kind of thing which we're doing. So um, basically what we're doing is we're saying cost to reach K or DP of K for I is basically for all J such that A of J equals A of I plus 1. So the cost to reach 0 from, let's say, the fourth element is equal to value of 4 plus 1. So value of fourth element plus 1. So all the positions J such that we get a 3, right? All the positions J such that we get a 3. And then we first add the cost from J between J and I. So to go from J to I, we add that cost plus the cost of J. So the cost to reach K, fine. And the cost for A of I equals K, this will simply be 0. Fine. So for the fourth element itself, like for all the occurrences of 4 over here, the cost is simply 0 because you've already reached 4. Okay, so this is going to be our, let's call it idea 1. Okay. Now what is idea 2? Our idea 2 is going to be, we only need to check uh, values just to my right, just to values, okay, values of A of I plus 1, just to the right of A of I, or just to left of A of I. And what do I mean with this? If I go back to the diagram, so in this diagram, let's take a different color. So if we are at this particular 2, I just need to check between this 3 and this 3. Similarly, if I am at this position of 1, okay, I need to check between this 2 and this 2. I will not consider this 2 because it's in red. I will not consider this 2. And what is the reason? I'll tell you the reason for this idea. The reason is, let's say we have 4, 4, 2, 5, 4, 3, 4, 3, 2, 2, 4, 5, 2, 1, something like this, right? So let's say this was our array and we are at the 4 over here. So we only need to consider this 5 and we need to consider this 5. There is no answer which would involve taking this 5. At least that won't change our minimum answer. And why is that? Because see, if we go here and we satisfy our 5, right? And let's say the array went up to 6. So let's say there was a 6 somewhere here, right? So if my 6, I needed to go back this side, then of course it is better for me to take the nearest 5 on the left. And even if I have to go more to the right to reach my 6, right? Even if I have to go more to the right to get a better cost, it doesn't change if I start from here or if I start from here. So basically, I only need to check the left and the right, immediate left, immediate right, for which is the next value I get. So for 4, I need to check the 5 on the left and 5 on the right. For 3, I need to check the 4 on the left, 4 on the right, and so on. And that is going to be our idea. Similarly, for 3, to calculate the cost of 3, I just need to check this 4 and this 4. So what will happen will be cost of this 3, or cost at this position um, will be cost at this position plus the distance. So the distance between these two is 1 plus the cost over here. The distance between these two is 3 plus the cost over here, whichever is giving me minimum. I'll greedily store that minimum. So you could say this is a dynamic programming idea. So with this, our problem is mostly solved. So with idea 1 and idea 2. And what is our algorithm? Our algorithm is going to be something like this. We can store a map map like this, right? Which will store for each number like 1, 2, 3, 4 up to k. For each number, actually we can make this a vector itself to save time complexity, since we know that all k will appear at least once. So yeah, we could have vector of vector int as well, but I in my code I wrote it as map. You can save time complexity and make it vector, right? And for each k, we can know when it appears. So if we know that 1 appears at position 0, 5, and 8, so we can say that 1 appears at position 0, 5, and 8. Our map will look something like this. 2 appears at positions 1, 3, 4, 7, and 3 appears at positions 2 and 5, 9, and 4 appears at only one position 6. So we can store these. Fine. Then what we can do is cost of all the positions at 4. So cost of all these positions, cost will simply be 0, right? Because that's the highest and we have already reached 4. Now for 3, for each element, we will find the nearest 4. Okay. So here says there's only one 4. So simply we will add costs of this. So cost at 2 will be simply difference between 2 and 6. So cost at 2 will be 4. Cost at 5 will be difference between, so 1, 9 and 6, 3. Okay. So now what about at 2? So at 2, what will be our cost? Or we can also call this our DP. Well, there is a 2 at position 1. What is the nearest 3 to this 2? To the left, there is nothing. To the right, there is this. So the minimum cost will be 5. Similarly, for 3, we need to check for the 2 which appears at position 3. So there is a 2 which appears at position 3. We need to check which 3s appear just to the left and just to the right. So we can see that there's a 3 at position 2 and there's a 3 at position 5. So we take this position, which is 1, the distance, which is 2, and we also take cost of 3, cost of this 3, right? So sorry, cost of at this position, cost at this position. We add these two and we take minimum and we store that as this one's cost, and so on. So then what happens is for each element, we have computed the value which we wanted. We computed the value for min cost walk to k starting at this element. So for each element, we computed a min cost walk to k with this method. And then finally, what do we need? Finally, we need to, if we start at a non-one element, we need to go and start at the nearest one, right? So this is again a very similar idea. We already have the positions of 1, and we know position of 1 is at 0, 5, 8. We know positions of 1, and we know that 1 occurs at index 0, 1 occurs at index 5, and 1 occurs at index 8. So what we can do is for every element, so it's like 1 is here, at position 5, 1 is here, at position 8 also there is a 1. So for every index, which is here, when we do a loop, we can consider the left position of 1 and the right position of 1. Obviously, we don't need to consider some position at the extreme, like after this, because of the same reason as above. We're greedily picking the nearest ones on either side. And what we will do is we'll simply output cost of this position. So let's say cost of 0 plus, let's say our I was equal to 3, right? So distance between position 0 and position 3 is 3. So this is one option. And let's say this is position 5. This will be cost of position 5 plus distance between 3 and 5 is 2. So we can take minimum of this, and that will be our answer for this element. Similarly, for every ith element, we can find the one before, one after, and we can print it out. Now, how to do that, right? How to find element before and after, element x, x plus 1, before and after element x. So if the value is x, element with value x. So we need to find this. Well, for this we can use, since we are storing it as a map of into vector, or we're storing it as a vector of into vector, and the vector is already being stored in sorted order. Since if you observe, when we insert the indexes, they will already be pre-sorted in sorted order. So all we need to do is we can use binary search, or in C++ we can use upper bound and lower bound functions. So we can do upper bound. So the next element will simply be the upper bound. If we want next element of 3, it will be upper bound of 3 in this array. So it will be 5 and upper bound minus 1. So upper bound and upper bound minus 1. These two iterators will give us from k equals 2 to k equals 3, like which two elements we need to consider for the costs. So the one on my left and one on my right, we can get using the upper bound function. So let us put it all together. What are we doing? We are saying that our cost we are computing by just checking just to the left and just to the right, which value is just greater than me. And I will compute the cost from there, and I will use upper bound and lower bound function to compute. So let us decide to write the whole code and what it looks like. So the code, we create, let's say, a vector of int to store for each k what is the position, or the way I have done it is used map. So it will just change the time complexity by a log factor, not much. And for each value of k, so first we'll take from the input array, right? So we'll obviously have a vector itself. This is our map. So as we are taking input, take input of all a of I. As we are taking input, what we will do map dot map of a of I dot pushback I. So we know that this element of value a of I occurred at position I. Fine. So then we have filled our map and we have filled our vector. And what we can do is for elements in our map, right? So for elements in our map in reverse order. So first we're going to try k equals 4, k equals 3, k equals 2, like we're going that way. So yeah, first we need to make a cost vector. So we'll make a cost vector, and initially we'll set cost of everything as infinity, since we want to minimize. So we'll set cost as infinity. We can also call this dp. We can also call this dp. So this is kind of a dynamic programming approach, or it is kind of a greedy approach, whichever way you want to see it. For me, it seems like a mix of both. So yeah, what we do is for elements in the map backwards, basically. So the ones with larger values first. Okay, yeah. So for the one with the value k itself. So map of k, all elements, all I in map of k, we set cost of I as 0 because they've already reached the end. Then what we do for, let's call it k dash, which goes from k minus 1 to 1, which goes from k minus 1 to 1. We calculate the values for all the indices in map of k dash. So for each index in map of k dash, so for I in map of k dash, for every index in map of k dash means every index which has this particular value, we will try to binary search. Let's call it L or R in left and right in map of k dash plus 1. Take minimum of the two. So what will this look like? This will be something like cost of I will be the min of I minus L, the difference between I minus L, plus the cost of L. So let's say that was the position of the one which was just before, and the distance between I and R plus the cost of R. So we take the minimum of these two and we continue on our way. So once this loop is done, we have the distance from every element all the way to k. So all we care about is the 1. So all we care about is cost of the positions at 1, right? So these positions we care about. So then for every I from 0 to n, we need to find the answer. So we make a vector called answer, which is empty for now, right? Then again, we search for LNR, binary search LNR in map of 0, sorry, map of 1. We're trying to find the just left 1 and just left R. And our answer again becomes minimum of I minus L plus cost of L, I minus R plus cost of R. So this is the cost to go to the 1, and from that 1 to go all the way, to walk a trail all the way to K. And then, yeah, so this will be answer of I. And we can simply print our answer. Simply print answer vector. So what is the time complexity? If you didn't get it yet, no worries. We'll go through the code once, which might make it clear. Let us discuss the time complexity first. So since I'm using map, the time complexity will be increased a little bit, but with vectors, it will be fine, I guess. So here we're simply taking input and we're doing pushback. So assume that we used a vector instead. So I'll take with respect to vector over here, because ideally you would use a vector and make the time complexity less. So this would simply be big O of n. Then here, what are we doing? We are going for all I in the map. So basically, we are only visiting each element exactly once, because in each element is added exactly once into our map. So therefore, we are visiting each element exactly once. Even in these two loops, each element is being visited exactly once. And here we are doing a binary search. So this will give us a log n factor, right? So this part of the code is n log n. These two loops are big O of n together, not n squared. And this part is log n, so n log n. And then again, for each n element, we are binary searching the one before and after. So again, this part is also n log n. And then printing the answer is O of n. So the final complexity is n log n. All right. Okay. Let us have a look at the code. It is pretty much as I described. We input our vector, we create our map. For each element, we push back the positions that element occurs. Here I have my distance vector, or you can call it my DP vector. Here I call it distance next. So it's the distance to the next step in our path. And then for all values where it is k, this distance will be 0 since we already reached our goal. For all the other values from k minus 1 to 1, here I'm just making a temporary vector over here just because I used a map, so I don't want to waste map access, like pay log n every time. Otherwise it becomes n log n. This way it will stay n log n, I guess. So yeah. So for each element that has value kk, I find, the upper bound in the map kk plus 1 array, and then I find the left point and I find the right point, and I check what is the distance over here, and I minimize my distance to the left and to the right. And then finally, once all my distances are computed from 1 to k, from 2 to k, from 3 to k, all of those have become computed. And I only care about from 1 to k, in fact. Then again, I go through all the indices from I equals 0, I equals till I equals n. I find the occurrence of 1 to the left. I find the occurrence of 1 to the right. I take the minimum cost of both of them. And finally, I print out my answer. I print out this whole vector. And that is how you solve E. Some DP and greedy ideas and some logical thinking and observation. So it is a fairly simple, like if you're good with binary search and greedy and DP ideas, then it should be fairly fun. Okay. Any doubt, you can put it in chat. Otherwise, we will be ending the session now. Uh, Thank you very much, everyone, for attending, and see you next time.